lesson 1.4, okay? Finding limits by analytic methods. Some of what, I kind of sometimes forget what you guys haven't learned in limits. So sometimes some of the things that I've said, I'm like, you guys question, I'm realizing, oh, we haven't really learned that yet. Okay, so each day we're learning a little bit more about limits. If you only observe the graph of a function, it can be misleading when finding the limit of a function. In this lesson, we explore how to find limits using algebraic techniques and limit theorems. So we're going to use a few limit theorems, but this is about, these type of questions would be questions you have on a non-graphing portion of the AP exam, or no calculator portion, because it would be doing it without a graph. Okay? Some methods that we're going to talk about. We're going to talk about direct substitution. We've already done that a little bit. That's just when if x approaches 1, you plug 1 into your limit. We have some basic limit theorems we're going to talk about. I've already talked about 3 a little bit. Factor/cancellation technique, being able to factor and cancel something. I've already hinted at that some. The conjugate method. If you have a fraction that's kind of nasty, we'll talk about rationalizing the fraction, whether it be, and sometimes that can be rationalizing the numerator. We're going to talk about 2 special trig limits that they fall into that category of things you just need to know walking out of AP. Okay? And we're also going to talk eventually about something called L'Hopital's rule. Looks like Hospital's rule, but it's pronounced L'Hopital's rule. And there's an alternate spelling for it too. But that we actually don't hit till Unit 3 because we have to know how to do derivatives before we can talk about L'Hopital's rule. Okay? So, all different ways to talk about limits. Now, substitution theorem. If f is a polynomial function or a rational function, then the limit as x approaches c of f of x is equal to f of c. So that's saying that that limit is equal to the function with the c value plugged into it. Provided that if f is a rational function, the value of the denominator does not equal 0. Important note here, always try direct substitution first. Okay, that's always a go-to method, is can I plug the number in? The problem is you're going to run into catches. Okay, if you get something like 0 over 0 or infinity over infinity, those are what I refer to as indeterminate forms, the goal will be to simplify the expression using some type of algebraic technique and then try substitution again. And that's a big piece of what we're going to work on here at the beginning. Okay? Now, I was short on screen space today, so I'm going to take this and enlarge it a little bit, and we're going to work here. Okay. Find each of the following limits analytically, and they're suggesting we use direct substitution. So, on the first one, the limit as x approaches 2 of 3x squared minus 5x plus 4.
Plug in 2 for the x, right?
Yep, plug in 2 for the x and go from there. And that's, again, a method you can usually use to get started. So 3 times 2 squared minus 5 times 2 plus 4. We all agree? Okay, that's what I have. Okay. B, the limit as x approaches 2 of x cubed plus 1 over x plus 1. We're always going to try that first. Okay, and once we plug the 2 in, we're done writing limit. It's no longer, you're taking the limit by plugging the 2 in. Does this work? Three? Okay.
Well, I just kept it 9 over 3.
Which technically would be correct, you know. Were you just not thinking about it being 3?
No, I just didn't want to.
Okay. What about C? What if I say this is a no calculator problem?
I don't remember what it is, but I know that E goes with the natural log somehow.
Okay, fair enough. Does that make sense? It goes with it somehow, you don't remember how? So what is the base of a natural log?
E,
Base.
It's E.
Yeah.
So we had a rule when we did log stuff, and I know it's been a hot minute.
Because doesn't it, if it's E and E, doesn't make it like 1?
Yeah. So if the base of the log and the inside base are the same, officially we say it's equal to the exponent. What's the exponent?
Or
An invisible 1. So that is a 1. Now, that's one of those things you need to know. Now, can you use the calculator at this point in your life to try and remember and figure it out? Yes. But if you do the natural log of E on your calculator, you're going to get 1. But, moving forward, just throughout the course of the year, work to know that. Which, I don't know, should I be the bearer of bad news now? Some of our early quizzes and tests are going to be non-calculator. Okay? So, okay, so what do we have then if that's the case? Natural log of E?
1/3E.
And that's what I would say you're probably leaving the answer as. Because E is a number, yes. And we can't go any further with
Natural
it.
log E/3E is correct too. So. What didn't you say?
I know, I'm debating. It's a numerical value.
I mean,
So, I think maybe.
I should make all these one-steppers really.
So,
Don't even.
okay.
do
Um,
numbers.
Okay, what about D?
Just call it the answer. It'd just be the cube root of 8, which is 2.
And while yes, okay, cube root of 8 is right, there are times where you need to be able to recognize that that doesn't stop at 8. The cube root of 8 is 2. So,
I didn't really, I just went straight to 2.
that's fine. I show more work than I need to at times. You guys know that.
Yeah.
Okay, what about E?
So it's going to be sine of pi over 3, basically. If you plug in the pi over 6, it's going to be 2 pi over 6 or pi over 3. And let's see if I can remember it off the dome.
Or is that numerical?
I don't think that one qualifies as numerical.
Hang on.
And that's I need to do some looking back because I don't remember for sure. I feel like you're expected to go one more step.
It would be square root of 3 over 2.
Agree, disagree, not sure yet?
That sounds right.
It's either that or 1/2. I'm pretty sure it's square root of 3 over 2.
Fair enough. That would be my thought, is
Yeah.
it's one of the two.
I was trying to draw a triangle in my head.
It is square root of 3 over 2. So is that how you do that one, a triangle?
Yeah,
Is
because
that
I
what-
never took the time to memorize the chart. I mean, I guess I can, but
Yeah.
just
Well,
a lot
and-
of numbers, especially when you get the cosecant and or the sine.
Yeah, see, I don't remember those three. I just flip. I have sine, cosine, tangent mostly memorized, and then I just flip them. Or I have quick ways to get to them. I don't memorize secant, cosecant, cotangent, all I just flip them. So, one thing I will say there, if you ever feel like it, I've never watched it, never taken the time to figure it out, but there's supposedly some hand trick
Yeah.
you can do with the trig functions. There's YouTubes about it,
I didn't learn the hand trick for the multiples of 9 or not till like last year.
See, I never heard that until like last year too. I think,
I never learned it.
yeah,
I couldn't even tell you what it is right now, to be honest.
I learned it last year. That's the only reason I know. Okay, what about F?
Should be log of 3. Yeah, 5 plus 4, which would turn into log of 3, 9.
Oh, there's
That's your answer.
Keep going. What do you know about 9?
Left, right, middle. That's all I know.
It's 3 squared.
Never met.
And log base 3 of 3 squared is equal to?
Cancel out the 3, so it's equal to 2.
Okay. Now, it's those pesky, trig functions, log rules. Those are things we've got to remember, throughout the course of the year. And that's part of the reason that don't just grab the calculator for everything. It's tempting, but don't. Okay. Okay. And I know Logan was questioning this the other day. When it says topic 110, realize we haven't changed lessons. That's just a topic reference number to, I don't know, it's not even some set of standards. I can't remember. It's some set of listing. It's what she used. So, process for finding discontinuities of a rational function from pre-calc. In other words, discontinuities. When we talk about discontinuities, I'm talking about holes and vertical asymptotes. How did we find holes and vertical asymptotes without a graph? Without a calculator, basically.
Holes were what? Equal to 0? It's like the x plus blank equal to 0.
And where did that x plus blank come from?
If they were like canceled out in like a fraction.
And vertical asymptotes were anything or the denominator equaling 0.
Yeah. Okay. So based on that assessment, in both cases, we have to look at the factors, right? So if I'm talking steps here, what's the process? The first thing I'm going to say is factor the numerator and denominator and simplify. Okay, so that's going to be my step 1 here, or of my process, is to factor the numerator and denominator. Oh my gosh, I can't spell. I don't know if I'm spelling these right or not today. So factor the numerator and denominator, then simplify. Okay. You have 2 options then. Okay. When factors cancel. When a factor cancels, you guys know it as a whole. And whole is still acceptable words, but you also need to know it as a point discontinuity. Okay, and I think I've talked about that a little bit somewhere. So a point discontinuity occurs when factors are removed or canceled, and then x minus a number, so x minus a equal to 0. So that's the second part I'm going to write. It's a point discontinuity occurs when factors
Cancel.
I would say cancel. It says are removed, but I'm happy with cancel. And then
And the remaining one is equal.
And it's when
0.
x minus a equals 0 is how I'm going to write it. Okay. The other option you have, and actually, might want to put, what was this one? This one was your whole. The other one we're going to do is a vertical asymptote. So you have that physical reminder. But this is a non-removable discontinuity, I think is what I want to say here. Yeah, a non-removable discontinuity. And this one occurs if factors don't cancel in the denominator. occurs if factors don't cancel in the denominator. And again, it's that x minus a equals 0. So I just used the word non-removable discontinuity and then point discontinuity. Back in pre-calc, maybe algebra, we didn't use the word point discontinuity, if you recall. That one was a removable, if you need to remember what that vocabulary was. I feel like it's not out of the realm to see removable, also thrown into calc stuff. So, okay. Okay. You can perform the same algebraic analysis. Okay, so this was kind of what we did when we were trying to graph something, look at our discontinuities. You can perform the same type of algebra to find the limit of the removable or point discontinuities and the non-removable or infinite discontinuities. That's another word I should probably put up there. So pair these up, right? Removable or point discontinuities, non-removable or infinite discontinuities. Because at this point, I'd say be familiar with all of it, right? Okay, just know what the words mean. Anyways, what we can use here is our factoring method or our cancellation technique. So we've already talked about this a little bit. First of all, what should be our go-to? Go-to method, what we've already talked about today, is trying to just plug a number in, yes? So let's plug a number in. Not plug just any number in, but what are we plugging in here? 2. Okay, I'm going to put this down below here. We plug 2 in. Let's see what happens.
Why do we have to plug it in?
What was your question?
For this, why would we have to plug it in if we're just going to look to cancel?
Well, I'm showing you why we would look to cancel. Okay. What did we just get?
0, 0.
0 over 0. But I'm going to tell you for 0 over 0 every time. Indeterminate form, try another technique. You don't get to stop at 0 over 0. You don't get to automatically say does not exist. Because in all honesty, more often than not, it probably does exist. Okay? So, I'm going to say that this is, we're going to go up and do this up above here. Indeterminate form. Try another technique. Okay? So, that's why we have these other techniques, because when you go to plug in, substituting the limit in doesn't always work. Example A. Plugging in 2 didn't work. It gave us 0 over 0. So, we need a plan B. Plan B, I'm going to look at that. I'm looking for options. Does it look like those pieces factor?
Yep.
Okay, factoring is always a good thing because good things can come out of factoring. They don't always, but they can. Now, I haven't actually taken the limit yet, so I want to make sure that I keep writing the word limit. Limit as x approaches 2. And I'm going to factor. Are we okay with this factoring? Okay, what can happen?
those twos can cancel.
We have a factor that can cancel. So I'm going to rewrite my limit here without those. So now this is equivalent to the limit as x approaches 2 of x plus 3 over x minus 4.
Plug in the two.
What?
Plug in the 2.
And now we've cleaned it up. We're ready to plug in the 2. What happens when we plug in the 2?
You get 5 over negative 5 halves.
Did it work now?
Yep.
Yeah, now it worked. Okay, now we have that negative 5 halves. Okay, so 0 over 0. It just tells me you hit a roadblock, find another way around. Okay, as we are learning limits, let me mention, you'll notice I kept writing limit for a few steps here, didn't I? I kept writing limit here because all we'd done is factor. It was still a limit. I kept writing limit here because all we'd done is cancel. It was still a limit. I quit writing the word limit here because it's no longer a limit because what did I do? I took the limit by plugging the 2 in. So that's just a key point. You have to remember, when do I use limit and when do I quit using limit? Make sense?
And just to clarify, if it was limit as x is approaching 2 and then x squared plus 6 minus that, and then another limit in the denominator, it would have just been 0.
We would have been stuck if it was a limit over a limit.
Yeah.
Well, I mean, we would have been stuck in a way, but our limit rules allow us to put it together, though, too.
Okay.
Which then allow you to, make it one fraction and work with it that way.
Okay.
Okay. So, okay. Moving on. Maybe. Okay. Graphically, looking at the function, and you'll notice this is the same function from above, we see that just because it's undefined as specific x value doesn't mean we can't find the limit. The Hoover Dam construction example. That was the one I just, they had the 2 pieces meeting there, okay? Use the graph of the function to determine the value of each limit below. So the limit as x approaches 2. According to my graph, what is that?
Your limit intersection. Oh. Function. We put negative 5 halves. But...
Okay. It was negative 5 halves above, yes. Does that make sense based on the whole here? Okay. As x approaches 2, you're approaching, it doesn't matter that that's a whole. You're approaching that value. It doesn't have to exist at that point. Okay, so like we know from up above and how the graph says it is negative 5 halves. Now look at these other 2 pieces. The limit as x approaches 4 from the right. What about that one?
X approaches 4. Infinity.
Yes? Okay, as we approach 4 from the right, I'm following the graph. You're going up along that vertical asymptote, so it is positive infinity. What about the limit as x approaches 4 from the left? Okay,
Yeah.
so we're approaching from over here. Now we're going down towards negative infinity. Now, I was looking to see, I'm going to throw in my own question.
X approaching 4.
Quit reading my mind. I'm just going to use f of x here because I don't want to rewrite the fraction. But the limit as x approaches 4, what's that going to be?
No.
Do
9. Yeah.
Yeah, you're going 2 different ways, right? It's not going to go the same way, so that is a good old D and E.
I understand that.
Okay? The visual helps sometimes, doesn't it? But here's the deal, you don't always have the visual, so we have to know both. Okay, algebraically finding limits of functions at undefined values. Consider what happens when you try to evaluate this limit using direct substitution. Well, we tried to evaluate it up above, okay?
Isn't that gonna work?
Okay, and when we tried to evaluate it using direct substitution, up above we got 0 over 0, right? Now, and what I will say is another option that you're going to get when you run into problems, infinity over infinity. We haven't gotten to that in terms of, what we're doing yet, but that's going to be the other problem that's going to become indeterminate forms.
I feel like more we could have just written, you'll get the wrong answer.
Okay, continuing. Talks about the top of the next page. Remember, when you get an indeterminate form, and that says 0 over 0 or infinity over infinity, your goal is to algebraically manipulate the expression in an effort to remove that hole that's causing it, okay? Then try the direct substitution again. We're going to look at a few techniques here.
Yeah.
What'd you say?
So we're becoming manipulators.
Exactly what I was thinking.
Lovely. Okay, so finding one-sided limits. If you look at that graph, there was a vertical asymptote at x equals 4. And we just talked about, I was kind of showing you ahead, right? But the fact that it was going to not exist because we're going 2 different ways. Well, how can we determine this if we don't have the graph here? And what we can look at here is so the limit as x approaches 4. Pick a value to the right of 4 and then analyze the simplified function. Now, when I say pick a value to the right of 4, I'm not talking about like picking 5.
4.001.
Exactly. I'm talking about picking something very, very small. Okay? So, now keep in mind, okay, first of all, you wouldn't use this form. What was our simplified form? Was it x plus 3 over x minus 4?
No, I don't remember. Something like that.
Based on what I'm seeing in my notes, that must be what we had into that.
Yeah.
Yeah, it was x plus 3 over x minus 4. That's what it factored to. So if we're picking a value from the right, okay, 4.1, 4.01, 4.001. The more zeros,
I usually
the
just go 2 zeros.
better understanding.
I
Okay, so if we're going to do that,
just go 3 decimal places, basically.
okay,
If it's the 9s, I do like 3 9s.
okay. So if I'm picking that number to the right, what are we doing then? 4.001 seems to be the popular opinion. Okay. So on top, what do we get?
7.001 over 0.001.
Okay. Now, you have both positives, yes? Okay. On top, you have a number of 7. And that's a positive number. Not really that big of a number, but it can grow bigger, yes?
It's going to get a lot bigger if we divide it by that.
Okay. Now, in this case, we're doing basically 7 divided by 0.001. What happens when you take a number like 7 and you divide it by a decimal 3 places
It's
like
almost
that?
like multiplying it by 1,000, isn't it?
Yeah.
It is. Okay. What if instead we made this 7.0000001 divided by 0.00001?
It'd be huge.
It's getting bigger, right? What are we approaching? Infinity. Okay. So that's the idea of knowing that, and you guys seem to be on board with this, so that's good. When as we approach 4 from the right, we're getting to tinier and tinier decimals. Okay? And you're dividing by a tinier and tinier decimal, which is going to make that top number explode. Okay? And do keep in mind, this was an easy one because we were doing a positive divided by a positive. Now let's try and do this piece real quick.
So we got on the other one? Yeah.
It is, yep. No coincidence.
No, I
Okay.
figured not. I was just
Yeah.
wondering.
So now we're approaching 4 from the left. It's still some number plus 3 and some number minus 4.
So like a 3.999
So are we doing 3 nines?
is what I'm doing.
Okay. On top, you're going to get 6.999 divided by on bottom.
Okay, so just
Point
negative
0,
Oh.
0, 1, negative.
So on top, we have about the same as last time. You have about 7. On bottom, you have about the same as last time, 0.001, except it's
Hello.
negative.
If you need a drink after school, the machines by the
What's
waitress
it gonna equal?
are stocked and ready to be purchased. Thank you.
Okay. What's this going to equal?
Negative infinity.
Okay. We're going to be at negative infinity this time because we ended up with a positive divided by a negative. It's still the idea, though. Forget the signs. It's still a solid number divided by a tiny decimal. And it's getting more and more tiny decimal. Okay?
And then one of the last problem on the notes.
Okay.
Full page, by the way.
Yeah, I saw.
We will
Page
stop
29.
there and pick up tomorrow. This official